Hi everyone, the topic of my presentation is an empirical study of the MRI waiting time. Currently, 546 Canadians are diagnosed with cancer each day, and currently 214 Canadians die because of cancer each day. Magnetic resonance image, also known as MRIs, can help the doctor diagnose a patient with cancer much sooner. However, the rapid increasing demand left the technology behind. As we can see from the animation, the number of arrivals is significantly higher than the hospital's capability of handling them. Therefore, a queue is formed and congestion occurs. People spend precious time waiting in the queue while they can be treated much sooner. There are two reasons that's causing this bottleneck in this queue. The first one is due to the limited capacity of the MRI scans, and the second is improper queuing management. Hundreds, even thousands of people waiting in the queues for days, weeks, even months, while the precious and already limited MRI capacity is wasted due to improper management. So, how do we solve this problem? Currently, many mathematical models proposed, and they aim to find a solution to this problem. However, in their process to find an analytical solution, many constraints are imposed on their model. But many of the constraints are incompatible to real-world requirements. That's what's inspired me to conduct my research, a data-driven model based on mathematical foundations and compatible to real-world application. Therefore, I propose 3 optimization policies. The first two policies I propose is called accumulation policy. So what is accumulation policy? Well, it's policies which give the patients different accumulation functions. Under each function, patients accumulate their weights. And when an MRI scan becomes available, the patient with the highest accumulated weight is selected to perform the MRI scan. The first method is called weight accumulation function, in which an initial value is given to different priority groups. The significance of an initial value indicates that high priority groups are always considered first, and their short target dates are always met. However, due to the significant initial value and different accumulation rate, many of the lower priorities are often neglected. That's what inspired me to the second kind of accumulation, priority accumulation. After the lower priority groups has waited in the queue for a significant period of time, they are promoted to a higher level where they can accumulate weight much faster. So instead of a static priority, a time-dependent dynamic priority queue is proposed, and therefore the lower priority group can receive treatment faster. One problem with majority of the mathematical research and my 2 optimization policy is to assume an omniscient point of view. That is, we schedule the patient on their day of arrival. However, this is highly unlikely in the real world due to the time needed to prepare the patient, the MRI scan, and the nurses. Therefore, it inspired me to my 3rd type of policy, advanced scheduling. Under advanced scheduling, patients are given prior warning before their MRI scans so they can be ready. So how do we exactly do this? Well, we divide the capacity into 3 categories. The first category is for high priority patients that arrive on the day of operation and need timely treatment. The second one, and the more important one, is allocated to scheduled patients. In this category, patients are scheduled to perform on a certain day, and on the day of the surgery, they are definitely treated. If by end of the day, we still have leftover and unused allocation, we pick patients from the waiting queue and treat them accordingly. As we can see, if we schedule further ahead, there's some capacity lost and lack of information due to increase the number of patients as exceeding their target. However, as we see from the table, with the increased number of days we're scheduling in advance, the increase in the number of patients exceeding their target is not that significant. So it's up to the hospital to decide how many days are they willing to schedule ahead and how many patients are they willing to sacrifice. As we can see, increasing capacity is significantly costly, but just by providing a rigid and scientifically management queue, we can reduce the number of patients exceeding their target date from 73% to less than 35%. That means we can treat the patient sooner, we can scan the patient sooner, and together we can treat cancer sooner. Thank you.